In 1887, Heinrich Hertz discovered that when light shines onto the surface of a metal, electrons are emitted, which is known as the photoelectric effect. The following figure indicates a typical setup for observing this effect. Light of a sufficiently high frequency F illuminates the surface of a metal, causing electrons to be ejected. These photoelectrons, as they are called, are accelerated through a potential difference and collected at the positive plate, thereby creating a flow of current between the two plates. As long as the light of this frequency or higher continues to shine, the current will be maintained. Let's consider some very important characteristics of the photoelectric effect. First, only light with a frequency above some threshold frequency, F0, will cause electrons to be ejected from the metal, and this is true regardless of the intensity of the light. Let's make a plot of the maximum kinetic energy of the ejected electrons versus frequency. Notice that no electrons are ejected for frequencies below the threshold frequency. Above the threshold frequency, the energy of the ejected electrons is directly proportional to the frequency. Now imagine that light with a frequency above the threshold shines on the metal surface, so that electrons are being ejected. What we find is that the maximum kinetic energy of the ejected electrons remains constant, even if the intensity of the light is increased. Classical physics predicts that the kinetic energy of the ejected electrons should increase as the intensity of the light increases. However, this does not happen. Also, we would expect that if we used very low intensity light, that it would take a long time for the electrons to build up enough energy to be ejected from the metal surface. However, this doesn't happen either. Even if the light intensity is very low, electrons are still ejected from the metal surface almost instantaneously, as long as the frequency is greater than F0. In 1905, Einstein presented an explanation of the photoelectric effect that took advantage of Planck's work concerning blackbody radiation. He assumed the energy quantization was a fundamental property of light and matter. In his photoelectric theory, Einstein proposed that light of frequency F could be regarded as a collection of discrete packets of energy called photons, with each packet containing an amount of energy E given by E is equal to h times F, where h is Planck's constant. The light energy given off by a light bulb, for instance, is carried by photons. The brighter the bulb, the greater the number of photons emitted per second. In order for the electrons to be ejected from the metal, they must absorb the energy from the light that shines on the metal surface. Einstein described this process by considering that the photons in the light striking the metal give up their energy to the ejected electrons. By conservation of energy, these two energies should be equal. However, it takes a minimum amount of energy just to remove the least strongly held electrons from a metal so that it is free of the metal surface. This is known as the work function, W0, of the metal. The energy required for the work function takes away from the kinetic energy of the ejected electrons. From this analysis, Einstein was able to write the expression describing the photoelectric effect by applying the principle of conservation of energy. The above relationship shows that the kinetic energy of the ejected electrons is equal to the energy of the light minus the work function of the metal. The graph shows a typical plot of the maximum kinetic energy versus the frequency of the light. The graph is a straight line that crosses the x-axis at F equals F0. At this frequency, the electron departs from the metal with no kinetic energy. According to equation 29.3, when the kinetic energy max is equal to 0 joules, the energy h times F0 of the incident photon is equal to the work function W0 of the metal. This allows you to calculate the threshold frequency for a particular metal. The photon concept provides an explanation for a number of features of the photoelectric experiment that are difficult to explain without photons. It is observed, for instance, that only light with a frequency above a certain minimum value, F0, will eject electrons. If the frequency is below this value, no electrons are ejected, regardless of how intense the light is. Furthermore, the maximum kinetic energy of the ejected electrons remains constant for a particular frequency, no matter the intensity of the light. Whereas the photon model of light explains the photoelectric effect satisfactorily, the electromagnetic wave model of light does not. Certainly, it is possible to imagine that the electric field of an electromagnetic wave would cause electrons in the metal to oscillate and tear free from the surface when the amplitude of the oscillations becomes large enough. However, if that was the case, then higher intensity light would eject electrons with a greater maximum kinetic energy, a fact that experiment shows is not true. Moreover, in the electromagnetic wave model, a relatively long time would be required with low intensity light before the electrons would build up a sufficiently large oscillation amplitude to tear free from the surface of the metal. Instead, experiment shows that even the weakest light intensity causes the electrons to be ejected almost instantaneously, provided the frequency of the light is above the minimum value f0. The failure of the wave model of light to explain the photoelectric effect does not mean that the wave model should be abandoned. After all, it correctly describes interference and diffraction effects. However, we must recognize that the wave model does not account for all the characteristics of light. The photon model also makes an important contribution to our understanding of the way light behaves when it interacts with matter. However, a photon is different from a normal particle. A normal particle has a mass and can travel at speeds up to, but not equal to, the speed of light. A photon, on the other hand, travels at the speed of light in a vacuum and does not exist as an object at rest. The energy of a photon is entirely kinetic in nature, because it has no rest energy and no mass. To show that a photon is massless, we rewrite equation 28.4 for the total energy E as the following. The term square root of 1 minus v squared over c squared is 0 because a photon travels at the speed of light when v is equal to c. Since the energy E of the photon is finite, the left side of the equation above is 0. Thus the right side must also be 0, so m equals 0 kilograms and the photon has no mass.